Welcome everyone. Today we're going to talk about numerical models. These are some additional preliminaries before we dive into optimization algorithms. This is coincides with chapter 3 of our book. I'm not going to cover all the details that are in the chapter, but try to highlight, I think, what are some of the most important for our present discussion. Give me a second here to share my screen. Okay, there we go. Okay, so first I want to talk a little bit about some of the differences between analysis and optimization. You're all used to to some degree, doing numerical analysis, either writing, generally some both of writing or running a program to compute something, right? So this is something that we're familiar with. But for optimization, although we will use analyses, there are maybe some additional considerations that we should keep in mind. So one thing that's maybe underappreciated at the beginning is the optimizer is going to explore a much wider range, or perhaps strange combinations of variables that you would not. It'll also exploit weaknesses in the formulation. So for example, here's a simple truss structure. If you were to optimize that, I say optimize, but you were to manually try to change this and improve it, you'd start with a reasonable design and you would change things in proportions that kind of made sense, and the analysis would probably work. Now, if you're an optimizer, it's a black box. You may try some really crazy combinations where something is extremely thick, something is extremely thin, and if not properly bounded, you're going to try negative thicknesses, all sorts of things. And so we do have to think about constraints, but some things we can't necessarily constrain, and we need to make our analysis to be robust, that it can work well, even with odd combinations of things that you might not try. And this is actually important to the algorithm, this sort of exploration. It's a necessary feature to find a good solution. But it's just something that we have to be a little more careful. So in general, the analyses that we write, we just have to be careful. They're a little more robust than normal. And a good way to check this, as you have developed your tool, your little code, is to test it on a bunch of things. So maybe do some parameter sweeps where you vary things and plot them. Try some random combinations of inputs. Just make sure that you get reasonable results. Sometimes an analysis may accept the numbers just fine, but will give you nonsensical results, right? You may get negative drag or things that you know are not correct just because you weren't expecting these kind of inputs. And again, some of that we can address with bounds, some constraints on the problem, but not all of it. Okay, another challenge, or I should say rather consideration that we should think about with analysis and optimization is that an analysis, so let's look at this little picture here. Here's the analysis that we're used to. We usually run that dozens of times maybe, right? So we might create a plot and sweep things out, but an optimizer is going to put an input X, get some objective and constraints out. It's going to keep iterating. You can ignore this box for a second. We'll talk about this a little later today. But the optimizer is doing this iterative process. So rather than calling analysis once or dozens of times, it may call it thousands of times. This means that we have to think a little more carefully about the fidelity or the computational time of our analysis. For example, if we had a simulation that takes an hour to run, if we have to call it thousands of times, then we may be waiting, well over a month for this to finish, and that's not going to be acceptable. So that may mean that we have to pay more attention to the types of algorithms we use, programming languages we use, that they're going to be computationally efficient. We may have to reduce the model fidelity. We can't use perhaps our highest fidelities, although there are some tricks that we can use to actually use pretty high fidelity simulations, and that's something we'll talk about later in the semester. But in general, we'll often have to perhaps simplify, or at least spend a little more time thinking about the numerical formulation, that it's going to be efficient, that this is something we can iterate on many, many times. Another thing that's not often appreciated early on with just analysis versus optimization is what we might call the noise or precision of your analysis. So often if we're running a code, we only care maybe about a few significant digits, right? We're only going to report a few decimal places. Whether there's a bunch of decimal places, whether those are accurate or not, we don't really care. Or if we are plotting a trend, we're going to plot some discrete points. If a point fails or doesn't converge, that's okay. We just throw it out and just keep going. Or if there's a little bit of noise, it's not too big of a deal. For optimization, that can make things really challenging. For one, some of the algorithms require derivatives. And if the algorithm is noisy, like this blue line here, those derivatives are going to become nonsensical. And even if we don't require derivatives, depending on the level of noise, it can make us harder to predict the behavior and to converge well. So even in cases where it doesn't necessarily, or I should say, it's going to limit the type of algorithms at our disposal. So this was an example where we're working with a student where this was predicting drag of a wing that was behind a propeller. And the way that we were originally doing it was quite noisy, and that was making the optimization have a lot of problems. And so trying to figure out what's going on and finally narrowed it down to this. So we had to be a little more clever about it and formulate the numerics a little more carefully so that we could get a smooth output. Right, the actual physics was smooth. It was just a case where we had this discretized wing, and as the propeller moved along, it was hitting some of these discrete points. And as it activated them, we'd see these little jumps. So we needed to come up with a clever way to smooth that out. And even without those kind of, or these kind of things are common to all, in some degree, to all numerical problems. There's going to be numerical errors, and we'll talk about some of those sources in a little bit. But in general, we don't often go down to small steps and see that there is some noise, and it's just something we need to be aware of. This helps a lot if we know this up front, if we think about this up front. As we're developing our code, if we're thinking about optimization, we can do a better job about paying attention to some of these numerical behaviors, making sure our outputs are smooth, and potentially even providing derivatives, a topic we'll talk about a fair amount later on. Okay, so here's an overview of a process of a numerical model, not an optimization, but a numerical model. We have some physical system, so say this is an airplane that we're looking at, and we could do experiments, right? That's a different realm. Here we're talking about mathematical models. And so we first have to do some translation from our physical system to a mathematical model. So in this case with the airplane, and let's say we're interested in the fluid flow around the airplane, that mathematical model might be the Navier-Stokes equations. In every step in this process, we've introduced some error. Even here going to experiments, right? We've introduced some error. Here, even with the Navier-Stokes equation, we've introduced some error potentially. That may be a very small error, but say, for example, Navier-Stokes equations, we'll have some limitations if we're going at very high speeds where there's a lot of heating, or we're at very high altitudes where the separation in the air molecules becomes large. No matter what our model is, it's not going to be necessarily a perfect representation of the world. So that's one simplification here. And we hear these words validate or verification and validation. Validation is concerned with this part. How well does our model match real life experiments? So it'd be comparing to how we do with experiments. Okay, and I'll get back to that in a second. So the next step here, we have a model that are Navier-Stokes equations. That's a continuous set of equations. We generally are going to have to discretize this into some numerical model, right? Our computers solve things with some finite precision. Here in this little picture, you can see a lot of these little cells. This is a discretization. We're taking the geometry or the domain of this fluid and breaking it up into a bunch of little cells. You may not have done this, of course, for something as large as an airplane, but you've done this in other cases, like, for example, if you're doing a numerical integral, like, say, a trapezoidal rule or rectangle rule. The integral itself is continuous, but to solve in the computer, we had to break it up into a bunch of little chunks that we could sum across. So now we've introduced another error, this discretization error. Obviously, you know, these, if we have too big of segments, it's going to be highly inaccurate, but we can't have an infinite number. And so we need to consider that source of error. Now that we have a model, we're going to program it. And of course, we can introduce errors that way as well. Programming errors, we hope to do some tests and try to minimize that. And then as we compute the solver is going to have its own limitations, how far or how tightly we can converge the solutions and the accuracy. So this is the process that we're going to go through, or that one goes through in developing a model, although we sometimes don't think about the breakup of these. We kind of lump it all together as just developing a tool. Okay, so I want to go back and I mentioned this briefly, but to be clear about these two words here, these are our key things here. As we develop this numerical model, we need to do both verification and validation. And they're two different things. So validation, it's concerned with the accuracy as compared to real life, if you will. So we compare it to experiments. So the question is our model choice appropriate, this mathematical model? Do things represent reality close enough? Verification is about our implementation. So we have a given mathematical model. It's have we implemented it correctly? Meaning have we reduced discretization errors to an acceptable degree? Have we eliminated programming errors? That kind of thing. So it's not a question of whether or not this matches reality or not. It's a question of, does it match what the equations should predict? So both of these are important, right? We need to first verify, make sure what we're actually trying to model we've done correctly, or no programming errors, or the numerical errors are not too significant. And then we want to make sure that that model is a reasonable representation of reality, and that's the validation piece. Okay, so let's talk about some of these sources of numerical errors. And to do that, we're going to have to talk a little bit about how a number is represented in a computer. And so here's the challenge, right? A number is really can be a continuous thing with an infinite number of digits. But on a computer, we can't represent numbers with an infinite number of digits. We have to use some finite number of bits. So we use bits to represent numbers. A bit is going to be a 0 or a 1. And, you know, there's a bit of a challenge because we want to represent a wide range of numbers, but we also want there to be small enough steps between them. For floating point numbers, these numbers we're going to use most of the time, the most common representation is what's called double precision. You may have heard of that. So we use 64 bits in double precision. Write that down here. So double precision, that's 64 bits. So that means for a single number, we're going to use 64 of these ones and zeros to represent a number. And this is typically done this way. So let's say X is a number I want to represent. We're going to use we use a scientific notation that allows us to represent a wide span of orders of magnitude, which is important. We have what's called the significand times 10, or sorry, not 10, we're going to use base 2 because these are bits, 2 to the exponent. Okay, so we use base 2 because we have bits that are just 0 and 1. This allows us to represent a fairly large range of numbers, typically like -10 to the 308th power, all the way up to +10 to the 308th power. If you go outside this range, you get what's called overflow. You may have seen this like on my kids do this all the time with like, you know, these little small calculators. They'll push a number, start multiplying something, you just keep pressing equals, so it just keeps multiplying, gets bigger and bigger, and then pretty soon it gives a nan, right? You're trying to compute numbers that are outside the range of numbers it can represent. Okay, so one important thing here is what's called machine precision. This is an important concept to know, and this just tells us what is the smallest number, not the smallest number that we can represent, the smallest difference between numbers. So it's a measure of the accuracy that we can get for a given number. So one way to capture that is we could say, if I took any number, but let's just say 1, for example, and I added epsilon to it, that the machine precision would be a number that once I added it to a number, I'd get a different number that I could represent. So let me try and break that down so it makes sense. Let's say, for example, we only had 2 bits to represent a number. Okay, I'm going to draw these 2 boxes here, right? And let's use base 10 for now because that's what we're used to, right? We use the numbers 0 through 9. So I could put a 0 through 9 here, and 0 through 9 here. The smallest number, or the smallest difference between numbers that I could present, or in other words, my machine precision would be 10, that's the base, to the minus 2. That's the number of digits, number of digits I have here, okay? Or number of bits, I guess. They're not really bits here, they're number of digits. So 10 to the minus 2 is the smallest number I can use because I've only got, 2 numbers here, right? So I could say 0.56. The next number could be, for example, 0.57, but I can't represent 0.562, right? Because I only have 2 numbers. And to represent 0.562, I would need 3 numbers. So I'd have to just round it to 0.56, either truncate or round it, right? So my machine epsilon here would be about, 0.01. That would be a number that if I added it to any of these, I could get the next number. But if I added something smaller, like 0.001, nothing would happen, right? So that's a representation, or that's an important thing because that tells me the resolution I can get. All of my numbers, if this was all I had, are only going to be accurate to about 0.01, right? I don't have any more accuracy than that. So erase this real quick. So for in a computer in double precision, I said we had 64 bits. Typically we use 1 for the sign, 11 bits are reserved for this exponent, and then 52 for this significand. And so I've got 52 numbers. So it's kind of like that example I gave here. Remember, we said, so if I have 52, I've got base 2. So each one of those can be a 0 or 1. And there's 52 of them. So the smallest difference that I can resolve, this is my epsilon, it's about 2 times 10 to the minus 16. Okay, so that means that's the smallest difference between numbers that I can resolve. Anything smaller than that is a difference, or that's about the accuracy that I can get. So that's why you may hear, or you may even notice this, when we see double precision, we get about 16 digits. If you were to look at a programming language, and some of them like MATLAB don't generally show you this unless you type out format long and see all the digits, but the number is represented by that many digits. So we can't, I may have a number that I want to capture to 32 decimal places. I can't do that. It's, or I should say significant figures. I can have 16 digits that have a bunch of zeros in front of them, but I can only have about 16 significant figures here. So this is an important number to remember. It's not so important necessarily to remember, how many bits are here, exactly how it's represented, but this idea that I can only have about 16 digits for double precision is something that will, come into play several times. So there are various sources of numerical error that can exist because of this. The textbook talks about a few of them. I'm going to highlight one that's a bit more insidious and something that's going to come to bite us later. And this is what's called subtractive cancellation. So here's an example of this. Imagine I have this number, and it's a number with a bunch of digits, and you can see I've got 16 digits here. These are the things that I can represent. So I've got 16 boxes, and they're all different numbers or whatever. They don't have to be different numbers, but there's 16 things that represent the accuracy of my number, and I store that in variable A. Now in variable B, I store another number, and it happens to be almost exactly the same except for these last 4 digits. So for example, let's say this was 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, and then these last 5 digits were different, and this one was the same. 1, 2, 3, 4, 5. So all these ones in gray were exactly the same numbers. These ones in white were not the same. When I subtract them, I get a whole bunch of zeros, and I only have a few digits remaining. That means I went from having numbers that had 16 digits of accuracy to now only a few. I lost a whole bunch of resolution. So just to give a small example, let's say I only had 5 digits. and A was, let's say, 0.12342, but B was 0.12341. Now, A minus B is going to be 0.00001. I have a number with only one digit worth of accuracy. Now, if I was, this number is really an infinite number with a whole bunch of digits here, and this one's an infinite number with a whole bunch of digits here. If I could represent all of them and I subtracted them, I'd still have an infinite number of digits here and be fine, right? It would really be like 0.0000, maybe it was 9, 8, 6, 5, a whole bunch of numbers, right? But those all had to get truncated or rounded. We call this round off error. And it happens with every operation, addition, multiplication, division, but those are usually smaller errors that accumulate. Subtraction can be, if the numbers are very close together, can be a very significant one. So these are just things to be aware of, and we'll talk about this again later, as we'll see what will come up for us. Here's another example of this noise that I was talking about earlier, right? So normally with the analysis, we might look at this from a very macro level and say, oh, okay, this looks good. And because I only plotted like, say, 10 points here or whatever, it looks like a nice curve. But if I was to plot a whole bunch of points really close together, I might see there's actually quite a bit of noise. Partly this is because of various errors. Round off is one that we just discussed. Round off means like my digits that have an infinite number, I have to chop it off and only keep 16 digits of precision. Truncation is another source of error. Truncation is it's kind of like the example I talked about with an integral. It means that I have something that really is an infinite number of operations, like that integral is an infinite sum, and we've chopped it off into a finite sum, so we get a truncation error. It would only really be accurate if I had an infinite number of divisions. And then another form of error is what's called iterative error. So this is where I have iteration loops. We'll talk about one in a minute. If I have to iterate on something, I'm trying to converge it towards some value or to some reducing some residual. That can also introduce other errors. Of course, there are also programming errors. That's not a numerical thing. That's just bugs that we have introduced in our code. And optimizers are very good exploiting those. So we have to be extra careful about that and make sure that we've tested our analysis. It's good practice before any optimization. Don't just take your analysis and throw it in the optimization. Do what I would call kind of a manual optimization. Explore it a bit, try some different combinations of things, look at your outputs, do things make sense? Maybe make some plots where you vary some of the parameters and look at the behavior. You really want to do that to make sure things are going to make sense, because if you just throw out the optimizer, it's likely that things won't go well and it'll be hard to know why. So it's good to kind of do some of the exploration first before you just throw it out there. Okay, switching gears a little bit, I want to talk about two more topics. One is this idea of implicit equations. And you've seen this before, but I just want to maybe remind you of it. Maybe you haven't seen exactly this way. So an explicit equation, these are the ones that we like and we're used to. Explicit is when I say, for example, f equals x squared, okay? I can just, if I know x, then I can just directly compute f, okay, simple. Here's an example of an implicit one. Let's say I can say u equals the sine of u plus x. Okay, so if I gave you x, I said x is equal to 1, I can't write down a formula that just gives me directly u, right? Because u appears on both sides, and I can't actually solve this equation for u and say u equals this stuff, which doesn't depend on u, right? All my inputs. So this is what we would call an implicit equation. You'll have seen this before in some different contexts, potentially. If you were in the aircraft design class last semester, there's an example where we were doing a rocket, and the fuel weights that the rocket required depend on how much structure there was, the structural weight. But the structural weight depends on how much fuel you need. So there's kind of this iterative dependence. It's an implicit equation. So often we need to iterate to solve these. And we're going to write this common way is that we always move everything to one side. We write this in a residual form. So I could say, for example, u minus sine of u plus x equals 0. We can do that with any implicit equation. We can always move everything to one side, and we just call this a residual equation. And so this term here, we would call this the residual r, and it's going to be a function in general of both x and u. And x, those are going to be our inputs. X is going to be inputs. U, then those are what we're used to. U is a new thing here. That's what we'll call a state variable. Okay, use a state variable. R is a residual. Okay, and the difference from the explicit equations is that these state variables are things that I cannot explicitly solve for. I have to iterate some way to figure out what they are. And the residuals, these are these equations that I'm trying to drive to 0. Once I make this equation 0, so for example, let's just say I was trying to do this by guessing. I put in a guess for u. That's one way I could do this, right? I could put a guess for u, plug it into both of here. If it gives me 0, great, I solved it. If not, I try a new guess for u, and I keep trying guesses until I solve it. So I'm trying to drive that residual to 0. That's how I know that I now have the correct state variable. So as a diagram, one way to think of this is that I give it some input x. I have this box now, it's my residual equation, and it depends on u, right? And I iterate inside there, and once I'm done, then I know what the right value of u is. So again, in this example, I plugged in 1 for x. I have to iterate to figure out what u is, hopefully a better method than just guessing a whole bunch of things. But once I get that residual to 0, I know what u is that satisfies it, and I spit that out. Okay, so these implicit equations, there are many reasons why these are important. First, let's step aside, not the optimization context, but these occur a lot in just numerical modeling. Many of our codes are explicit, right? We just compute this line and the next line just follows from that one, and we're only using variables from above. But often we're going to have these things that are implicit, like the rocket example is one I talked about. In the present homework, there's even one where we're solving this truss structure. It's a lot like problems you've done you may have done in a structures class, a machine design class where you use the finite element software. So in finite element software, it's the same thing. You can't actually compute the stress directly. We have to solve a system of equations to figure out what the deflections are. Those would be the states. We're trying to figure out what the deflections are that satisfy my boundary condition for all the forces and the boundary conditions like clamped ends and things. I put those boundary conditions and I'm solving this residual equation to figure out what the deflections are. And once I have the deflections, that's my state, I can compute stresses. So there's a solver that occurs there. I don't know if you've ever looked at maybe some bigger problems with those finite element software, you may see that it's actually doing some iterations. So this often happens in analysis, that there are these things we can't compute directly, we have to iterate. I mentioned this guess method. This is not a great method. Some other methods, a very simple method is what's called fixed point iteration. That's a slight improvement. Well, not slight, it's a much better improvement over just guessing a bunch of stuff. But it starts with a guess. You start with a guess, so I know x, that's just an input. I put in a guess for u, but I only put it here on the right-hand side. And that's going to give me a new value of u. So then I take that u, I put it back, and it's going to give me a new value u. And I put it back, and I just keep going. I put that in a for loop. And usually this will converge pretty well. It's not the most robust method. It has a tendency to sometimes blow up or bounce around. So there are better methods. It's also not the most efficient. One you're familiar with is Newton's method, and I'll review that in a second. But Newton's method, you'll have seen in a numerical methods class. This is also a way to solve a systems of equation, or solve an equation like this, where we're trying to find a root, right, where something equals 0. This is a more efficient approach to this. Okay, so that's for numerical methods. It also happens in optimization. This is the same diagram I was looking at earlier. We ignored this box before, but now we're going to put it in. That doesn't always exist, right? We may have only explicit equations, but sometimes we have these implicit equations. And so around the optimizer, well, I should say, actually, there are two ways to do this. One is that these residuals, we can actually just stick them in as constraints. And then this whole box goes away and we give the job to our optimizer. We say, in addition to the normal constraints and things I want you to do, I would also like you to solve these equations for me as constraints. And we can do that. And there are sometimes some advantages doing so. But the more common approach is that these set of equations, we converge inside the analysis. So the optimizer, it's opaque to the optimizer. This is all just a big box. The optimizer, we still just give it X and get out the objective and constraints. But inside the analysis, we're running these for loops, we're running these Newton solves or whatever to figure out our state variables to get the objective and constraints and go back to the optimization. There are some implications of this that we'll talk about later on, but some that we've already discussed today is that because we have this, as compared to regular analysis, we need to make sure these loops converge really tightly so we don't have noise. We need to make sure we're using efficient solvers so that our optimization isn't taking too long, because we're not going to run this just once, but many, many times. And if we want to get derivatives, there's some additional things we need to think about here, which we'll talk about later in the semester. Okay, so last thing, let's review Newton's equation. Sorry, Newton's method, rather. And I'm going to review the 1D version, and then we're going to talk about it in ND, because that's something that we're going to need in some of our optimization methods. So let's talk about it in 1D. Let's say what I really want to solve is this residual equation, right? And it's the x's don't change here. They're just inputs for this residual. It's the u we're trying to solve for. So I'm trying to find when this equation equals 0. Remember, we could always move everything to one side, so it's quite general to say we want the residual to be 0. So let's say I'm at some certain point u. So my current iteration is at u, and we're going to use this notation for iteration k. It'll be a superscript in parentheses. This means iteration k. So this is just, let's say, a starting point, or at some point in my iteration. This is my first guess. Likely, if I just plug this in, it's not going to give me 0, right? So I want to find a way to choose what my next value of u should be. I want to choose this intelligently. I want a better guess. I don't want to just, pick something randomly. I want a good guess for where I should go. So the idea is we could use a Taylor series. Let's do a Taylor series expansion. So I'm going to take R. I'm going to start at the point that I'm at, and I want to take some step delta U away. And I want to figure out what's a good delta U to take. So if we do a Taylor series, right? So when I say equals here, we're going to expand this into a Taylor series. And if you've forgotten Taylor series, there's a bit of review in the appendix in the book, but it's going to look like this. We're going to get the first term, right? Just R of U, just evaluating it. And then I'm going to get delta U times the derivative, R prime, right? The derivative of R evaluated at that point. You might normally have seen as X naught the first time you've seen Newton's method, if we're using f of x, plus, second derivative, third derivative, fourth derivative, and so on. We're gonna just truncate it there. Okay, we're gonna keep it simple. And I want to figure out when this thing equals 0. So ideally, the goal here is I'm already at this point. I want to choose my delta U so that this just equals 0. Okay, and it's not necessarily going to get me there exactly, because I just eliminated a whole bunch of terms. If I could solve for it with all the terms, then of course I could get there. But if I include all the terms, I'm not going to be able to solve it explicitly. But with only these two, I can solve it and give me a good guess. It says delta U should be equal to, right? I move this over to the other side and divide by that. I get minus R divided by R prime. Okay, so I take my initial guess, or whatever point I'm at. I evaluate the function, I evaluate the derivative of the function, I divide them, put a negative sign in front, and that tells me the step I should take. And so in other words, my new value of U is going to be the old one plus this step. And this is Newton's method. You've probably implemented this before in, say, a numerical methods class. It's also going to be let's just see an example of this to remind you. So again, If this was only a linear equation, then this would work perfectly. But for a general equation, we truncated a bunch of terms. And so this isn't going to get me there in one step, but it's going to give me a pretty good guess. And I'm going to iterate through this until I satisfy some convergence criteria. Maybe that delta U becomes really small. So here's an example of this. This black curve, this is the R, this is my residual function. And what I want to find is where it equals 0. So where it crosses the x-axis here. My x-axis is U, and I'm going to start with this guess. U of 0, that's my initial guess. Now the Taylor's theory, remember, it's going to use my function here. It's also going to use the derivative, so it's using the slope. And the interpretation is that it's going to linearize the function. It's going to say, okay, if I was at this point, I know nothing else except for the function value and its slope. I'm going to continue this as if it's a line and see where it intersects 0. That's going to be my guess for where we should go next. And of course, if the actual equation was a line, we'd nail it perfectly, but because it's not, we have to iterate. But it gives us a good direction to go, so, and a good step. So here's that line, intersects here, that gives us a new guess. We evaluate the function here and its derivative. It gives us a new slope, we end up here. Now we evaluate the function derivative again, we end up here, and we might take another couple of teeny little steps here till we converge and we get our solution for U, in this case, 0.54. This is a much better method generally than fixed point iteration. It converges quadratically. And roughly what that means is that we double the number of significant figures each iteration. So if I had 2 digits of accuracy, I could go to 4 and then 8. And so it very quickly will improve in accuracy. So it's an efficient method. Finally, let's extend this to n dimensions because we're going to actually use this in optimization. And we're never going to optimize with one variable. We're going to optimize with many variables. So we want to make sure we can use a Newton's method in many variables. So we'll come back to this in a week or two, but I just want to show it to you once so it's not too surprising when we see it again, so we can review it a couple times. So now, if I've got many variables, there's a couple things I have to change. I still want to find when R of, actually, I'm just going to write in terms of f here. Let's just say f of x. Okay, I want to find when f of x equals 0, but x is now a vector and f is a vector. And if these are a bunch of sets of equations, then there has to be equal number, right? If there's 5 x's, then there better be 5 f's, right? So I can solve this. Okay, so I still want to figure out what the next delta x is that I should take. But now I have lots of f's, so I'm going to write f's of I. This is just the ith equation. I'm still going to start at my xk. I'm going to start at this iteration, and I want to figure out what the delta x is that I should take. Okay, I'm still going to do a Taylor series. So again, the same idea is that I want to set this equal to 0. And I'm going to try to figure out what delta x should I take, what would be a good guess that I'm going to land at 0. But remember now, x is a vector, and so is f, or there are many f's. So doing the Taylor series expansion looks pretty similar. I get the function term, and now I'm going to get the derivative term. But the tricky thing here is that I have a bunch of functions and I have a bunch of x's. So I actually have to take a sum over all of the x's, and I'm going to have the derivative of my ith function with respect to my jth variable. So there are a bunch of them. And then I multiply by delta xj. Okay, so, and then of course there could be higher order terms, but we're going to neglect those. All right, this thing right here, we call this the Jacobian. Give it a symbol J, it's called the Jacobian. And we could also write it this way in a matrix notation. We could say plus J delta x, where delta x is now a vector. Okay, so in other words, in a shorthand, I've got f as a vector plus J delta x equals 0. So this is a vector, this is a vector, this is a matrix. Okay, and so I can solve delta x just like I could before. Let me rewrite this actually one more time. I could write it this way: J delta x equals minus f, right? And again, matrix, vector, vector. And this is a form that you've seen. This is just a linear matrix equation. We could have written the form AX equals B, right? That's maybe what we're used to seeing. And so we solve this as a set of linear equations. We could write it this way, although we would never do this in the computer, right? We could say it's J inverse times F, the invert of the matrix. We don't ever actually explicitly invert a matrix when we solve in the computer. If you're doing this, in, for example, in MATLAB or Julia, you would do something like, you'd use this backslash notation, or in Python, you'd use a linear algebra, like solve. You'd solve a system of equations. This backslash notation doesn't mean to do an inverse, it means to do a linear solve. Okay, but that's what we're doing. And so once we compute it, same idea, except for this is a vector now. We can update all of our x's at the same time. Oops, that's a k, plus this vector of delta x's. So if you go back and compare to the 1D, it's very much similar. Before we had a derivative on the bottom, and you could think of an inverse as kind of that same idea. It's a very similar thing, but we have to solve a linear system of equations to do this. Okay, don't worry if you didn't get that all. You can, I encourage you to review it, and we will discuss it again in a couple of weeks as we go to unconstrained optimization. But I would encourage you to review that. If a lot of this looks like you haven't seen in a long time, I go back and look at the appendix. Some of these things on Taylor series and Newton's method would be good to kind of brush up on a little bit. And yeah, please do send me any questions in the chat, and we'll see you next time.